Hey everybody, thanks for joining. Today, what we're going to talk about is the basics of social inquiry. So far in class, you've read notes on things like the philosophical underpinnings of the way the judiciary is constructed, a couple of modern philosophies on how the Constitution should be interpreted, and things like that. But as the syllabus says, and as I've said in some of the earlier notes in class, this class is really about the academic research on the behavior of judges. And as we move into that section of the course, I think it's fruitful to pause and talk about the nature of social inquiry, the nature of political science as a scientific enterprise, what that means, and how that applies to judges. So, how can we learn about the behavior of judges through the scientific and social inquiry enterprise? So, the goals of this lesson are first to talk about the goals of science. What is going on with science? What's the purpose? What are scientists trying to do? And the second thing is really a better understanding of how we apply the scientific method, how we apply science itself, how we take those goals and apply them to studying judges in a systematic way. And finally, I'm going to give you sort of a quick and dirty, little bit of a practical guide to how to obtain some information from scholarly research. I know a lot of students look at an academic article and sort of have a brief heart attack. Um, they see some numbers and some statistics and things like that. And I don't want that to be you. I'm going to give you a couple of tricks on how to learn from scholarly research. So I want to take a quick note on statistics. So following from that last point, let's talk about stats real quick. Look at the following for a moment on your screen and tell me what it means. Or obviously you can't tell me, but think to yourself, what does this mean? Okay. If you've taken Political Science 251, you should have some sense of an idea of what all that means. I'll give you about 5 seconds. Of course, you don't know what it means. You don't need to know what that means. I don't want you to know what that means. If you do know, good for you. But you do not need to know anything like that to succeed in this class, okay? This is not a statistics class. It's not a math class. In fact, Political Science 251 isn't even a prerequisite for this course. If you see something like that, maybe these complex equations, just ignore it, okay? It shouldn't affect your understanding of what's going on. So just kind of glance right over that stuff. My advice in this class is to avoid the trees and find the forest. I want you to take away the big sort of 30,000-foot view of everything we read. You don't have to know specifically how they estimate things or anything like that. So if you follow the theory and the findings that either do or do not support that theory, the best you can for every reading in this class, you're going to be just fine, I promise. Okay, so with that out of the way, let's move forward and talk about science. Well, what is science? I think a lot of us have an okay idea of what science is, but then we take a class called political science or some other social science. So the question is, can social science be science? We hear this differentiation between a social science and a natural science. Well, one definition of science is the intellectual and practical activity encompassing the systematic study of the structure and behavior of the world through observation and experiment. Well, by that definition, of course, social sciences and political science can be science, right? It is looking at the structure of various political institutions, the behavior of individuals in those institutions, and we do that through observation and experiment. So, by that definition, of course, the social science can be science. But here's why we have that difference, they're denoted differently, the natural science versus the social science. It's really hard to study people. It's really hard to study the social world. People occasionally have incentive to lie, for instance, or they may obfuscate the things they do. So that makes coming to conclusions about how the world operates when that world is social very difficult. And that's what separates the two sort of types of science. Um, I want you to think about why that might be, other than some of the instances that I just gave, and that is likely going to be part of your your quiz at the end of this the end of this lesson. So think about why it's so difficult to study people. The thing that unifies all sciences, however, is some of the features of science and the way we go about doing things. The goal of all science is to infer something about the world, to learn something about the way the world operates. One of the other very important features is that the procedures are public and hopefully can be replicated. If the procedures are public, if I engage in some scientific enterprise and describe it adequately enough, you should be able to go and do the same thing and hopefully get the same results. Now, this is a very important feature of science, the public procedures and the replicable procedures, because at least in my view, this is one of the public values of science. This is why we pay people to do it. Especially in recent years in politics, you see various websites like 538.com or Politico or the Washington Post Monkey Cage. You see these websites conduct these political analyses, and they do them very quickly. Something happens in politics, they have a story on it within the next couple of days, where it might take an academic researcher 6 months, a year, or what have you, to report similar findings. So you might be asking, well, what's the difference between blogging and researching? Why don't we just let the people who are faster do it? Well, the fact of the matter is that the knowledge that scientists produce is likely to be more accurate because of the public and replicable nature of the procedures. Those websites, they don't always tell you exactly what they're doing. They don't always tell you where they got their data, things like that. So the fact that the way the system is designed is for scientists to reveal all of that information provides some inherent value to the knowledge that scientists are producing. Okay, another feature of science. The conclusions are, by their very nature, uncertain. It is not a particularly scientific or academic thing to say, I know 100% certainty that the world operates this way. The conclusions are uncertain necessarily. And a lot of times we can actually estimate the degree of uncertainty. And that's something I'll get to a little later on in this lesson. Finally, and this is one that I really want to emphasize, science is the method. It's not the domain. Science is the way you conduct an experiment. It's the procedures you use in an observational study. It's not chemistry or biology or something like that. It's the way you go about analyzing anything. It's the approach, the rules, the tools that are used. All those things make something science. Another way to say that is science is the verb. It's not the noun. It's the action. It's not the outcome. Okay, so those are some of the important features of science. One of the most important features, one would hope, is objectivity. Remember a couple of lessons ago in notes earlier in the semester, we talked about things like psychological and cognitive biases, right? The anchoring bias and the recency bias. You may remember reading about the street lamps turning off when you're walking underneath them. One thing we noted several times in those notes is that those are unconscious biases. Okay, we don't know that we have them. And even if we do know that we have them, sometimes they're really difficult to avoid. They're sort of built into it. They're hardwired into us in many instances. Those same biases and many, many more influence scientific researchers, okay? Scientific researchers are not free from bias, but this doesn't make them biased. I know that sounds funny, but that's true. So here's a great question. Is objectivity in science possible? And you expect me to answer, yes, of course it is. No, the answer is absolutely not. Objectivity is not possible in science because objectivity is very difficult in humans. So if objectivity is not possible, what do we do? Well, think about a fact. Isn't a fact an objective statement about the world? 2 plus 2 is 4. That's a fact. No, a fact is just an idea for which there's broad consensus. If 50% of mathematicians said no, 2 plus 2 is 5, 2 plus 2 equaling 4 would not be a fact. It would be something that was disputed. But we use a base 10 numeric system, and in that, 2 plus 2 is 4. It's just something for which a lot of people agree, and that's what makes it a fact. In my view, broad consensus is as close as we can get to objectivity. So there's really no such thing as a fact. It's just a lot of people agreeing about the state of affairs. Objectivity implies an innate truth. We can't possibly know innate truths in science. Remember a couple of slides ago, I said science is necessarily uncertain. The conclusions are necessarily uncertain. Well, if we admit to uncertainty, we have to admit that we can't discover innate truth if it even exists. So the best we can do is consensus. That implies everybody sort of agrees about this thing and everybody's viewing things through the same lens. Okay, so I'm saying objectivity is not possible. You may think, well, what's the point? Let's burn the enterprise down if we can't be objective about it. If we can't even agree on things, what's the point? That all stems from, again, these innate human psychological biases. We believe the things we want to believe. We don't want to believe the same things all the time. People view things differently. One reason for this is because perceptions are inherently social. The information that's actually going into our brain depends on what we're doing socially. It depends on context and all these other things. Context very much matters for the way we perceive things. So it's not about believing the same thing necessarily. It's that we might actually be perceiving things in a different way without even knowing it. Here's a couple of examples. The first one's a YouTube link. I'll let you click on that on your own if you want, but I'll describe it briefly now. In the 1950s, this psychologist named Solomon Asch would bring a bunch of people into a room, maybe 5 or 6 people. One person was the actual research subject, and what they didn't know is that the other 5 people were what's called a confederate. The researcher placed them there and gave them instructions on what to do to set up so they could see what the one actual research subject did. So what the task was here is that a researcher would show a large, sort of poster board type thing with 1 line on the left side and 3 lines on the right side. And the 3 lines on the right side were labeled 1, 2, and 3. And each individual in the room had to say which of the lines on the left matched the length or the height or whatever of the line on the right. I swapped that, I'm sorry. Which one on the right matched the one on the left. And what Solomon Asch found is if the Confederates in the room were told to lie, to say, oh, line 3 clearly matches the one on the left, when of course it didn't, the actual subject would say that it did as well. So perhaps they just felt embarrassed that they believed it was a different line. But follow-up questions found that they actually began to perceive the line as being of a different length than their brain was telling them. They sort of questioned their own perception of the world based on what the other people in the room were saying. So go watch that YouTube video. It's a great video. There's also something called the minimal group paradigm. This is another example of perceptions being inherently social. Divide people into groups that are totally trivial. Light eyes versus dark eyes. This is a classic example. A teacher in the 1950s or 1960s, I can't remember, did this in her grade school classroom. And if you assign some distribution task, right? So you say, hey, here's $10. You got to give everybody, you got to give out all $10 in quarters or whatever. Basically, the person is going to give away the money to their artificially constructed group and not give any to the artificially constructed out group. So if I have dark eyes and we're artificially grouped together, I'm going to give all the money to the people with dark eyes and not give any money to the people with light eyes, even if I wouldn't have done that without that artificial group, right? So that's the minimal group. That grouping is light and dark eyes in this example. So your perceptions of who's good or who deserves something is based on totally fake, unimportant, trivial group lines. So what do these things tell us about the real world? These are just two examples. There's hundreds of great examples out there, but what do they tell us about what's going on in the real world? Well, like I said, context really matters. And second, not only does knowing context matter, but it's also important to know that context actually influences the things we believe, what we perceive, orientations towards other people, and all sorts of things like that. You might be asking, why the heck are we talking about this? Well, let me bring it back to the idea of the goals of science. The natural sciences can very easily, in most situations, control for certain contexts. In a laboratory setting, they can set the temperature, they can set the pressure, they can control for the various things that might affect, I'm not a natural scientist. It might affect how exothermic some reaction is. I don't know. In the social world, we can't change context. I mean, we can in certain situations, but a lot of times we can't. Think about something like sociological research. We can't change race. We can't change ethnicity. We can't change things like socioeconomic status as the researcher, right? Of course, people can earn more money or whatever, but the researcher cannot control for those contexts. Because we can't control the context, we have to design the process in such a way that makes it like we were controlling for the context. This is what science is, effectively. This is what we mean when we talk about scientific procedures or the scientific method. It is, in effect, changing the process in a systematic, controlled way such that we can isolate the thing we wish to make inferences about. In our class, the thing we wish to make inferences about is judges. So we need to, in a way, control the rest of the social and political world such that we can make inferences about judges. Okay, what do I mean by that? Well, what we do is we construct our method of thinking such that we set ourselves up to fail. So look at the following two statements and think to yourself, which one sounds scientific? Okay, the first one, I think caloric intake influences weight. I'm going to believe that until it's disproven. Or the second statement, I think caloric intake influences weight, but I won't state that until I have evidence for it. Obviously, the second statement is the more scientific of the two. But not only is that just a good way to hedge your bets, it's actually a way to change the process such that we don't come to incorrect conclusions. Again, scientists know they have inherent biases. They want to show the world that caloric intake influences weight. They're incentivized by that. They're excited by the research. So what they end up doing is structuring the process to avoid these biases. That is, we begin with statement number 2 instead of statement number 1. We set ourselves up to fail. We assume that X, here in this example, caloric intake, has no effect on Y, here weight, until there is sufficient evidence otherwise. To do the opposite, to say, I'm pretty sure X has an influence on Y, you got to disprove me, that is setting yourself up to succeed. And that's not changing the state of affairs in a way that allows us to make meaningful inferences. Another way to say this is that science has to begin from this place of skepticism. It necessarily begins with, I don't think there's a relationship, but I'll go see if there is. So a skeptical scientist has to recognize a number of things. First, not all beliefs are created equal. All right. Something like, oh, well, it could be, or who knows, are not good responses to a scientific claim or for supporting some specific belief, right? Even though scientists ought to be skeptical, they can't be so skeptical as to, in fact, be skeptical of skepticism itself, if that sentence makes any sense. Second thing is that extraordinary claims require extraordinary evidence. No good scientist would say something is impossible. Human levitation is a good example. Most scientists would never look you in the eye and say it is impossible entirely. And the reason for that is because it could happen. You never know. It just so happens that human levitation would go against all established laws of gravity. So they can say with some certainty that it's impossible. But to actually state that it was impossible is sort of a bridge too far. That's not what it means to be skeptical. A researcher has to keep an open mind, but as Bertrand Russell said, not so open that your brains fall out. There are limits, but to construct those limits in such a way that your mind is not open is problematic for a skeptical scientist. Okay. What does any of this have to do with judges? At this point, you might be worried you're in the wrong class, you're listening to the wrong lecture. Now, this has a lot to do with judges. Let me give you sort of the major point. It doesn't matter if you think judges should only use the law to make decisions, whatever that in fact might mean. It's just not true. I'm here to tell you, it's not true. Judges use ideology, they use political leanings, all these different things to make decisions about the law. All I mean to say is should does not influence does. Your ideas about whether judges should use the law exclusively do not change the fact that they use ideology. They use political pressure, things like that. Okay. Well, how do I know that judges use things like ideology? Well, I know because the scientific enterprise has suggested as such, and that skeptical setting ourselves up to fail has shown that to be the case. Well, we can't change context about judges. You know, we're not in the Senate. We don't get to confirm them. We can't control what information judges have. That wouldn't be fair to litigants. That would violate due process. And we can't trust their statements on how they decide. They're incentivized to lie and say, I only use the law, of course. So what do? We have to use the procedures of science to figure out what influences their behavior. We have to look for recordable, measurable actions. So when it comes to Supreme Court justices, a treasure trove of information is how they vote on cases. Something else is speeches they've given. What types of information do they include when they write the opinion, whether it's a majority or a dissent, right? We have to look to all those different things to sort of glean some information about judges. Let me be a little more specific. We start this sort of scientific portion of this class with the premise that politics either does or does not influence judicial behavior. The way a political scientist sets this up is he or she would say, we see a relationship between a justice's ideology and his votes. For example, a liberal justice votes the liberal way 90% of the time. The way we ask whether that's a meaningful, systematic relationship is, what's the likelihood that that observed relationship between ideology and votes is totally due to chance? Now, it's possible it's due to chance, but we have to estimate the probability that it's due to chance. The baseline assumption, what in the scientific tradition is called the null hypothesis, is that the relationship is, in fact, due to chance. It's a coin toss. It's no different than a coin toss. It's random. The only time a scientist would state that ideology influences votes, or which is called the alternative hypothesis or rejecting the null hypothesis, the only time a scientist would say that is if they estimate the likelihood of that relationship occurring by chance being very, very low. Let me state that a different way. If a scientist says the probability of the relationship between ideology and votes being random is 2% or 3%, that it's so low as to be very unlikely due to chance, then and only then do you come to the conclusion that X influences Y, or here ideology influences votes. Something that probably didn't occur by chance is often referred to as statistically significant. Now, all of these things have fancier definitions that you might get in your statistics class or your political science 251 or whatever class you end up taking. I don't think they're necessary here. So for this class, something that's statistically significant, it's enough to say it's very likely that that thing did not occur by chance. Now, you'll notice I'm hedging my bets. I'm not saying that thing didn't occur by chance. I'm saying it probably didn't occur by chance. That is the necessarily uncertain nature of the scientific inquiry. So again, let's take this another step. What does this have to do with this class? Well, we use scientific evidence to describe the behavior of judges in this class. So I think it's very useful for you to have this idea of where researchers are coming from. They're coming from this place of, well, I'm assuming there's no relationship between these two things, and I'm only going to tell you there's a relationship if I find evidence that there actually does seem to be one, and the chance of that being by chance are really low. The consequences of the behavior that we're going to describe in class, so for instance, ideology influencing votes, you can decide for yourself whether that's good or bad, whether it's good for democracy or bad for democracy, whether it's good for society or bad for society, good for the judiciary, bad for the judiciary. All right, that is a personal moral judgment. However, that personal moral judgment has no reflection on whether the evidence is accurate, whether the inference is accurate, or anything like that. Right. So that's a very important takeaway from today's lesson. The goodness and badness of the consequences we will describe are unaffected by and do not affect whether the inferences or whether the evidence is good. Okay. You know, we can have conversations about these things in class, and there will be writing prompts where you're asked to discuss whether you think those things are good or bad. But just because you think it's good or bad doesn't mean it's not true. Okay. That's an important thing really to take away here. So as we're sort of moving on and being a little closer to informed consumers of science, let's talk about a couple of terms you're going to encounter in various papers throughout the semester and how you can sort of navigate them. So having some definitions might help you. Okay, so let's start with a variable. A variable is just some characteristic or number or something that can be measured or counted. Examples are things like age, height, weight, political party, somebody voted, for whom they voted. In this class, whether a judge was appointed by a Republican or Democratic president, whether the judge is a man or a woman, whether the judge voted for the liberal or conservative part or outcome, or whether they voted for the respondent or whatever. A dependent variable is a variable whose value depends on that of another, right? It depends. That's pretty simple to remember. An independent variable, on the other hand, is a variable whose variation does not depend on that of another. So I'll give you an example. Weight does not depend on, let me start over. Weight depends on caloric intake, exercise, metabolism, and all these other things, right? Weight is the dependent variable here. It depends on those other things. Calories, exercise, metabolism, those things don't actually influence each other. Those are the independent variables. Okay. So those are some of the important terms. I just want you to be able to keep dependent variable and independent variable straight throughout the semester. Because this is not a statistics class, I do not expect you to be able to sort of always navigate the sometimes complex statistical modeling we're going to look at. But I do want you to be able to identify statistically significant results. So when a researcher says, I found X, Y, and Z, I want you to be able to look at a table or a figure or wherever and know where the evidence is that that researcher found that. Let's go back to those variables. Let's say a study determines that calories influence weight. So the more calories you eat, the more weight you gain. The question for you is, how am I supposed to know that that's what the study says? Well, here's a couple different ways. First of all, the authors are going to tell you the punchline. They're going to tell you what they find. So read the study, and you'll learn at least something about what the study says. The second way is a results table. I'll show you in a second how to sort of gather information from a results table. And then you can look at pictures, and sometimes pictures make very clear how big of an effect or whether there is an effect or something. And I'll give you a couple of tips and tricks here at 2 and 3 at results tables and pictures. Now, if any of you are statisticians, you may be about to roll your eyes, or your statistics professors may come to my office and tell me how wrong I am, but I'm going to give you a couple of quick and dirty tricks on how to help you throughout the semester at finding statistical significance. All right, so let's look at this table, okay? We see this thing here. We see in this first column all of the variables that are included in this model. So caloric intake, exercise, height, and metabolic rate are all predicted to influence weight. How do you know that weight is the dependent variable? It usually says in the table, sort of the label for the table. These are coefficients in this column, and these are standard errors. Usually, when a study includes a little asterisk next to the coefficient, as we see here, here, and here for caloric intake, exercise, and the constant, don't worry about what constant is for now, that usually means that that variable, that independent variable, has a statistically significant effect on the dependent variable, okay? So when you're looking at a table like this, look for the stars, look for the asterisks, and it usually means that the relationship isn't due to chance. Now, different papers have different things. Some of them have little crosses, whatever. It should tell you what each of them means, but as a general rule, you should be able to look for the stars, okay? So you see here I've crossed off all the information that doesn't have a star. You can still glean a lot of information without all of that extra stuff. Some of that extra stuff is important for, other people who are interested in the topic. But for the most part, if you want to know if caloric intake influences weight, look for that little star. Okay, identifying statistical significance with pictures, different story. I said earlier that we can usually estimate how uncertain we are or how certain we are using various statistical methods. One way of doing that is something called a confidence interval. I'm not going to go into the technical explanation, but you can think about it as a range of plausible values. Okay, so think about an ice cream cone, right? The average caloric intake of an ice cream cone is, 285 calories. I'm making that up. But you could obviously imagine that sometimes the guy at the ice cream store gives you a bigger scoop, and sometimes he gives you a smaller scoop. So we could say that the range of plausible values is somewhere between 260 calories and 310 calories, just because each ice cream cone is a little bit different. So the confidence intervals would be between 260 and 310. And the estimate, what we call the estimate, the average here would be 285. Okay. Now, if we take that idea and translate it to our story about calories and weight, think about imagine each ice cream cone makes you gain, on average, an eighth of a pound, 0.125 pounds. Now, sometimes it might be a little less. Sometimes it might be a little bit more because the ice cream cone, the size of the ice cream cone varies. So each one could make you gain between 0.085 and 0.155 pounds, right? That would be the confidence intervals, the range of plausible values. Importantly, for the little secret to finding statistical significance with pictures is that if the confidence interval range included 0, that is, if, let's say, the ice cream cone made you gain between negative 0.05 pounds and 0.15 pounds, you couldn't conclude that an ice cream cone leads to weight gain because 0 is one of the plausible values, right? So you could say, hey, how much weight does an ice cream cone make you gain? And you could say, well, it might be 0. If it might be 0, you can't conclude that there's any meaningful effect, okay? So let me show you this in image form. You see here on the, if you follow my little marker here, on the y-axis is weight gain, and on the, can't see it there, and then on the x-axis is ice cream cones per day, all the way from 1 up to 10. What a wonderful life that would be. What we see here is that for all values from 4 ice cream cones down, so from 1 to 4 ice cream cones, again from here to here, we see that this dashed line, that's one of the confidence intervals. It crosses 0 here on the y-axis. Okay, that means for ice cream cones 1 through 4, it's possible that you gain no weight. However, after ice cream cone 4, that is from here to here, this confidence interval thing, this dashed line that I'm highlighting right now, is above 0. That means at, let's say, 6 ice cream cones, let's follow it up, you could gain between this much weight and this much weight. So somewhere from like 0.15 to 0.5. All of those values are above 0. Okay. Our estimate is here that you gain about 0.2. But all the plausible values are from here to here if you're looking at my cursor still. Okay. Again, those values are above 0. That's how we know that there's a statistically significant relationship there. That's an easy way to use pictures. Now let's do another version of this same image. It's just represented a different way. Before, right, we have this line, so it's for each value of ice cream cone. Here, I'm only showing you 1 and 10. Here, for one ice cream cone, the value is a little bit above 1, but the confidence interval intersects 1. The confidence interval intersects 0 here on the y-axis. That means we cannot be certain that you gain any weight from one ice cream cone. However, if you come over here to 10 and look at this bottom confidence interval and trace it over here to the y-axis, we're pretty certain that some amount of weight is being gained if you eat 10 ice cream cones. It's somewhere between, let's say about 0.3 and 0.6, but those values are above 0. So that's how you know that it's statistically significant. Okay, this is the thing we'll finish on. Let's go to the idea of normative versus positive statements. Okay, a normative statement is subjective. It regards what should, what would, what could, or what must happen, what must be, what is good. Okay, a normative statement expresses a value judgment. Something is either desirable or undesirable, depending on how you feel. It's based on an assessment of what's good. We cannot verify that based on observation or experience. Okay. Basically, something that's normative is not measurable. We can't measure the good that comes from, attending, attending a study session in school. It's hard to measure what's good if there's no difference in test grades or something. An example of a normative statement: the world would be a better place if everybody whistled while walking. I think that's terribly false. Whistling's annoying, but we can't measure whether or not that's true. Normative statements, by that token, then cannot be false. They're unfalsifiable. We can never prove them wrong. Now, let's contrast this with a positive statement. Positive statements are objective. They regard what is, what has been, what will be. There's no value judgment here, right? We're not saying what ought to be. We're saying what is. They're based on assessments of what is. It's verifiable. We can observe or experience something and say, yeah, that's true. Because of that, they're generally measurable. An example here is when supply increases, price goes down. That's economics 101. Positive statements then can be false. We can prove them wrong. If somebody said when supply decreases, price goes down, that's wrong. That's just not how it works, and we can show that empirically. So I want you to take a look at the following sentences and think to yourself, are they positive or are they normative? So something like, a judge should only decide cases based on the law. That one's, of course, a normative statement. Judges only decide cases based on the law. Well, we can test that. We can measure it. That's a positive statement. It may be incorrect, but positive statements are allowed to be incorrect. Judges decide 75% of cases based on their ideology. That one is a positive statement. We can determine whether that value is correct or incorrect. Judges decide 75% of cases based on their ideology, which is damaging the country. So you can take a positive statement and append a normative statement to it, and then altogether it becomes a normative statement. Another one is judges are nothing more than partisans in robes. Well, that one's a little tough. It could be either. If you said this sort of with a nasty look on your face and we're making a value judgment, then it's a normative statement. But if you're sort of arguing that judges tend to vote with the ideology of the president who appointed them, well, then it could be closer to a positive statement. So all of these things, I hope you've really taken to heart in this lesson today, and I hope that they're going to be able to help you going forward as we're reading academic research, scientific research, and you're looking for things like statistical significance to determine does ideology influence a judge and how much and under what circumstances and all that type of thing. So thanks for tuning in, and